Gradations of matter. The main principle on the structure of matter, from the point of view of a new model of the universe, is the idea of gradations in this structure. Matter of one kind cannot be described as consisting of units of matter of another kind. It is the greatest mistake to declare that tangible matter consists of atoms and electrons. Atoms consist of positive and negative electrons. Molecules consist of atoms, particles of matter consist of molecules. Material bodies consist of matter. It cannot be said that material bodies consist of molecules, or of atoms. Atoms and molecules cannot be regarded as material particles because they belong to a different space-time. As was pointed out previously, they contain more time than space. An electron is much more a time unit than a space unit. To regard, for instance, the body of a human being as consisting of electrons or even of molecules is wrong, just as it would be wrong to regard the population of a large town or a company of soldiers, any gathering of people, as consisting of cells. It is evident that the population of a large or even a small town, a company of soldiers, consists not of microscopic cells, but of individual people. In precisely the same way, the body of a person consists of individual cells, or simply physically, of matter. This is not meant as a metaphor either, showing a gathering of people as an organism and individual people as cells of this organism. A whole series of unnecessary hypotheses fall away as soon as we realize the general connectedness and cohesion that follow from this definition of matter and of mass. The first thing that falls away is the hypothesis of gravitation. Gravitation is necessary only in the world of flying balls. In the world of interconnected spirals, it becomes unnecessary. Similarly, there disappears the necessity of recognizing a medium through which gravitation, or action at a distance, is transmitted. Everything is connected. The world constitutes one whole. Another interesting problem is disclosed at the same time. The hypothesis of gravitation was connected with observations of phenomena of weight and of falling. According to Newton's legend, indeed, the apple that Newton saw fall from the tree, these observations gave grounds for the building of the entire hypothesis. It occurred to nobody that the phenomena that were explained by gravitation or attraction on the one hand, and the phenomena of weight on the other hand, are totally different phenomena, having nothing whatsoever in common. The sun, the moon, and the stars that we see are cross-sections of spirals which we do not see. These cross-sections do not fall out of the spirals because of the same principle, by reason of which the cross-section of an apple cannot fall out of the apple. However, the apple falls to the ground, as though aiming at the center of the earth in virtue of an entirely different principle, namely the principle of symmetry. When we reflected previously upon the fourth dimension, there was a description of that particular movement that was called movement from the center, and towards the center along radii, and which with its laws enumerated is the foundation and cause of the phenomena of symmetry. The laws of symmetry, when they are established and elaborated, will occupy a very important part in the new model of the universe. It is quite possible that what is called the law of gravitation, in the sense of a formulation for calculation, will prove to be a partial expression of the law of symmetry. The definition of mass as the result of the motion of invisible points dispenses with any necessity for the hypothesis of ether or dark matter. A ray of light has material structure, and so has electrical current. However, light and electricity are matter not formed into atoms, but remaining in the electrical state. Returning to the concepts of physics and geometry, it must be said that the wrong development of scientific thought, that has led in new physics to the unnecessary complication of problems that were indeed simple in their essence, was to a great extent due to operating with undefined concepts. One of these undefined concepts is infinity. Infinity has a definite meaning only in mathematics. In geometry, infinity needs to be defined, and still more does it need to be defined in physics. These definitions do not exist, nor have there ever been attempts at such definitions that are worthy of attention. Infinity is taken merely as something very big, bigger than anything else we can conceive, and at the same time as something completely homogeneous with the finite, yet incalculable. In other words, it is never said anywhere in a definite and exact form that the infinite is not homogeneous with the finite. By this is meant that it has not been established what distinguishes the infinite from the finite, either physically or geometrically. In reality, both in the domain of geometry and in the domain of physics, infinity has a distinctive meaning that differs greatly from the strictly mathematical meaning. The establishment of different meanings of infinity solves a number of otherwise insoluble problems, and leads thought out of a series of mazes and blind alleys, created either artificially or through misunderstanding. First of all, an exact definition of infinity dispenses with the necessity for mixing up physics with geometry, which is a favorite idea of Professor Einstein, and the foundation of non-Euclidean geometry. It was pointed out earlier that the mixing up of physics and geometry, ergo the introduction of physics into geometry, or a physical revaluation of geometric values, all these rigid rods and non-rigid rods etc., that follow from an identical mathematical valuation of geometrical and physical values, is unnecessary either for argument concerning relativity, or for anything else. Physicists are right in feeling that geometry is not sufficient for them. In Euclidean space there is not enough room for them with their baggage. But the remarkable feature of the geometry of Euclid, and this is exactly why Euclidean geometry should be preserved intact, consists of the fact that it contains within itself an indication of the way out. There is no need to break up and destroy the geometry of Euclid as it can adapt itself very well to any kind of physical discovery, the key to which is infinity. The difference between infinity in mathematics and infinity in geometry is quite clear at first glance. Mathematics does not establish two infinities for one finite quantity, and yet geometry begins with this. Let's take for example any finite line. What is infinity for this line? We have two answers, a line continuing into infinity, or the square, of which the given side is a line. What is infinity for a square? An infinite plane, or the cube of which the given square constitutes one side. What is infinity for a cube? Infinite three-dimensional space, or a figure of 4 dimensions. Thus the usual concept of an infinite line remains, but to it there is added another, the concept of infinity as a plane, resulting from the motion of the line in a direction perpendicular to itself. The three-dimensional sphere remains, however a four-dimensional body constitutes infinity for a three-dimensional body. Furthermore, the problem becomes even simpler if we bear in mind that an infinite line, an infinite plane, and an infinite solid are pure abstractions. Whereas a finite line in relation to a point, a square in relation to a line, and a cube in relation to a square are real concrete facts. Therefore, remaining within the domain of facts, the principle of infinity in geometry can be formulated as follows: for every figure of a given number of dimensions, infinity is a figure of a given number of dimensions, plus 1. At the same time the figure of the lower number of dimensions is incommensurable with the figure of the higher number of dimensions. Incommensurability in figures of different numbers of dimensions creates infinity. All this is elementary. However, if we bear in mind the inferences to be drawn from these propositions, they will enable us to free ourselves from the influence of the wrongly interpreted Aristotelian principle of the constancy of phenomena. The principle of Aristotle is true only within the limits of the finite, and within the limits of commensurability. As soon as the infinite begins we know nothing, and have no right to assert anything in relation to the unity of phenomena and laws. Continuing these arguments we meet with another still more interesting fact. That is that physical infinity differs from geometrical infinity, as greatly as geometrical infinity differs from mathematical infinity. Or to be more precise, physical infinity begins much sooner than geometrical infinity. Furthermore, if mathematical infinity has only one meaning, and geometrical infinity two meanings, then physical infinity can have many meanings. That is to say, the mathematical meaning of incomputability, the geometrical meaning of the presence of an additional dimension or immeasurable extension, and purely physical meanings, namely difference in function. Infinity is created by incommensurability, but incommensurability can be arrived at in different ways. In the physical world, incommensurability can be brought about because of quantitative difference alone. As a rule, only quantities that are different qualitatively are regarded as incommensurable, and the qualitative difference is regarded as independent of the quantitative difference. However, this is exactly where the chief mistake lies. Quantitative difference brings about qualitative difference. In the mathematical world, incommensurability is created by the incomputability of one of the quantities compared. In the geometrical world, it is created either by the infinite extension of one of the quantities that are being compared, or by the presence in it of a new dimension. In the physical world, it is brought about simply by a difference in size, that sometimes even permits of calculation. All of this means that infinity in geometry differs from infinity in mathematics in being relative. Mathematical infinity is equally infinity for any finite number. But geometrical infinity has no absolute meaning. A square is infinity for a line, but it is merely bigger than another smaller square, or smaller than another bigger square. In the physical world, a large body is often incommensurable with a small one, and the small body bigger than the large one. A mountain is incommensurable with a mouse, and the mouse is bigger than the mountain. The reason for this is that in the physical world things are determined by their functions, function in the sense of purpose. The function of every individual thing is possible only if the thing itself has a definite size. The reason why this has not been noticed and established long ago is to be found in a wrong understanding of the principle of Aristotle. Physicists have often come upon manifestations of this law, namely that the function of every individual thing is possible only if the thing has a definite size, but it has never arrested their attention, and never led them to put together observations obtained in different domains. In the formulation of many physical laws, we find qualifications that the particular law is true only of medium quantities, and that in the case of larger quantities or smaller quantities the law changes. This law is still more clearly seen in the phenomena studied by biology and sociology. The conclusion from what has been said can be formulated in the following way. All that exists is what it is only within the limits of a certain and very definite scale. On another scale it becomes something else. In other words, everything and every event has a certain meaning only within the limits of a certain scale, when compared with things and events of proportions not very far removed from its own. A chair cannot be a chair in the planetary world. Similarly, a chair cannot be a chair in the world of electrons. A chair has its meaning and its three dimensions only among objects created by the hand of man, serving the needs and the requirements of man, and commensurable with man. On the planetary scale, a chair cannot have individual existence, because it cannot have any function. It is simply a small particle of matter inseparable from the matter surrounding it. As has been explained previously, in the world of electrons also a chair becomes too small for its function, and therefore loses all meaning and all of its significance. A chair actually does not exist in comparison even with things that differ from it much less than planets or electrons. A chair in the midst of the ocean, or a chair in the midst of the alpine ranges would be a point having no dimension. All of this shows that incommensurability exists not only among things of different categories and denominations, and not only among things of a different number of dimensions, but also among things that merely differ considerably in size. A big object is incommensurable with a small object. A big object is often infinite in comparison with a small one. Every separate thing and every separate phenomenon, in becoming bigger or smaller, ceases to be what it was, and becomes something else, something belonging to another category. This principle is still foreign to physics, both to the old and to the new. On the contrary, every separate thing and every separate phenomenon remains for physics what it was originally recognized as being. Matter remains matter, motion remains motion, velocity remains velocity. Yet it is precisely this possibility of the transition of space phenomena into time phenomena, and of time phenomena into space phenomena, that conditions the eternal fluctuation of life. This transition takes place when the given phenomenon becomes infinity in relation to another phenomenon. From the point of view of old physics, velocity, that was considered a generally understood phenomenon requiring no definition, always remained velocity. It could grow, increase or become an infinite velocity, and it occurred to no one to doubt it. Having only accidentally stumbled upon the fact that the velocity of light is a limiting velocity, physicists were forced to admit that all was not well, and that the idea of velocity needed revision. However, old habits die hard, and physicists were reluctant to surrender at once, admitting that velocity can cease to be velocity and become something else. So what did they actually stumble upon? They stumbled upon an instance of infinity. The velocity of light is infinity as compared with all the velocities that can be observed or created experimentally. Therefore, as such, it cannot be increased. In actual fact, it ceases to be velocity and becomes an extension. A ray of light possesses an additional dimension, as compared with any object moving with terrestrial velocities. A line is infinity in relation to a point. The motion of the point does not alter this relation. A line will always remain a line. The idea of limiting velocity presented itself when physicists hit upon a case of obvious infinity. However, apart from this, all the inconsistencies and contradictions in the old physics that were discovered and calculated by Professor Einstein, and supplied him with material for the building of his new theories, all of these without exception, result from the difference between the infinite and the finite. He himself often alludes to this. Einstein's description of the example of the behavior of clocks and measuring rods on a rotating marble disk suffers from one defect. Professor Einstein forgot to say that the diameter of the marble disk to which are fastened the clocks that begin to go at different speeds with the movement of the disk, according to their distance from the center of the disk, should be approximately equal to the distance from the Earth to Sirius. Or else the clocks must be the size of an atom, about 5 million of which can be put into the diameter of a full stop or period. With such a difference in size, strange phenomena can actually occur, such as the unequal speed of the clocks, or the change in the length of the measuring rods. But there could not be a disk with diameter equal to the distance from the Earth to Sirius, or clocks the size of an atom. Such clocks will cease to exist before they change their speed, though this cannot be intelligible to modern physics, which as previously pointed out cannot break free of the Aristotelian principle of the constancy of phenomenon. It cannot therefore notice that constancy is always destroyed by incommensurability. It can be assumed generally, that within the limits of terrestrial possibilities, the behavior of both the clocks and of the measuring rods will be quite respectable, and for all practical purposes we can safely rely upon them. There is only one thing we must not do: we must not set them any problems with infinity. All misunderstandings are caused by problems with infinity, chiefly because infinity is introduced on a level with finite quantities. The result will of course be different from what is expected. An unexpected result demands adaptation. The special principle of relativity, and the general principle of relativity, are very complicated and cumbersome adaptations for the explanation of the strange and unexpected results of problems with infinity. Professor Einstein writes that proofs of his theories can be found either in astronomical phenomena, or in the phenomena of electricity and light. In other words, he affirms by this that all problems that require particular principles of relativity arise from problems with infinity or with incommensurability. The special principle of relativity is based upon the difficulty of establishing the simultaneity of two events separated by space, and above all upon the impossibility of the composition of velocities in comparing terrestrial velocities with the velocity of light. This is precisely a case of the establishment of heterogeneity of the finite and the infinite. This heterogeneity has been spoken of earlier, with regard to the impossibility of establishing the simultaneity of two events, and Professor Einstein does not specify at what distance between two events the establishment of their simultaneity becomes impossible. If we insist upon an explanation, we will receive the answer that the distance must be very great. This very great distance again shows that Professor Einstein presumes a problem with infinity. Time is really different for different systems of moving bodies, but it is incommensurable, or it cannot be synchronized, only if the moving systems are separated by a large space which is actually infinity for them, when they differ greatly in size or velocity. That is, when one of them is infinity in comparison with the other, or contains infinity. To this must also be added that not only time, but also space is different for them, changing according to their size and velocity. The general proposition is quite correct. Every separately existing system has its own time. But what does separately existing mean? Then how can there be separate systems in a world of connected spirals? All that exists in the world constitutes one whole, and there can be nothing separate. The principle of the absence of separateness, of the impossibility of separateness, constitutes a very important part of certain philosophical teachings. For example, in Buddhism, where one of the first conditions for right understanding of the world is considered to be the destruction of the sense of separateness in oneself. From the point of view of a new model of the universe, separateness exists, but only relatively. Let's imagine a system of cogwheels, rotating with different velocities that depend upon their size, and upon the place occupied by each of them in a system. The system, for instance the mechanism of an ordinary watch, constitute one whole, and from this point of view there can be nothing separate from it. But from another point of view, each separate cogwheel moves at its own velocity, i.e. it has a separate existence and its own time or timing.